In this video, we're going to continue to look at secondary structure, and we're going to do that by looking at fibrous or fibrous proteins. And in general, you have two major classes of proteins, this fibrous or globular. And this fibrous proteins, they're usually protective or connective or supportive proteins. For example, we're looking at alpha keratin here. And alpha keratin makes up your skin, your hair, any horns, nails, or feathers. And these are what we call a coil. That is, it's just two coils wrapped around each other. And they're both left-handed. And if you look at alpha keratin, it has a repeat where A, B, C, D, E, F, G, where these represent amino acids. And what you see is that the A and D residues are always going to be hydrophobic. So when this alpha keratin comes together, you will always have the hydrophobic regions interacting with each other, and that's how you have such a strong connection. The hydrophobic effect will push these hydrophobic regions together to make this coiled structure. Now, if we look at alpha keratin, there's actually quite a few layers of order. So first, you just have this coiled rod, which is the dimer. You have the N terminus pointing in the same direction, the C terminus pointing in the same direction, and this is about 450 angstroms. This dimer will actually form with other alpha keratins, where the C terminus will point against another rod's N terminus for favorable electrostatic interaction here, and you'll have two sets of these forming together to make a protofilament. These protofilaments, these units of two, will be next to another protofilament, and this unit is called a protofibril. Then 4 protofibrils will come together to make a microfibril. Unfortunately, we don't know how this really looks. There's a lot still to be discovered about the structure of this. Now, when you look at alpha keratin, you'll see that there's a lot of cysteine residues, and these cysteine residues will have disulfide bonds. And the amount of cysteine depends on the role of this alpha keratin. So hair has a lot of cysteines because it is generally harder than something like skin, which is much more flexible than your hair. And it's interesting, when you burn hair and you get that stinky smell, that smell is from sulfur. That sulfur is from your cysteines. And we actually use the idea of cysteines having a lot of hair having a lot of cysteines when we do a perm. So normally your alpha keratins will be in disulfide bonds, and during a perm you'll add a chemical to reduce these disulfide bonds. You can then curl your hair and re-oxidize, forming new disulfide bonds, leading to this permanent curl. Or you could do the opposite. Let's say your hair is curly and you want it to be straight. You break these disulfide bonds, you straighten out your hair, you reform the disulfide bonds, now you have straight hair. That's how that works on a biochemical level. Now, another type of fibrous protein is called collagen, and alpha keratin was a double helix kind of, and this is a triple helix. You have 3 helical segments wrapping around each other, and they make up your bone, teeth, cartilage, tendons, matrix of the skin, and blood vessels. And it's actually the most abundant protein you have in your body, and the vertebrate proteins most abundant. Usually you have a repeating pattern in collagen. It goes glycine, something else, where X is often proline, Y is a special amino acid called 4-hydroxyproline, or prolol, or HIP. And the only difference is that it has a hydroxy group on carbon 4. That's why it's 4-hydroxy. Now, the interesting thing about collagen is that if you want to make this hip residue, you need vitamin C. If you do not have vitamin C, that is, you don't eat your fruits or veggies, you cannot make collagen. Therefore, your teeth, your bones, your cartilage isn't as strong anymore. We call this scurvy. So sailors hundreds of years ago on ships didn't have fresh fruit, so they would also often get scurvy, where they would see loss of teeth, pale skin, their eyes would get sunken. And British sailors, they beat scurvy by eating limes. So that's why sometimes you can call, or people call British people limeys, because they ate limes to beat scurvy. And actually, college students, about 10% of college students have early signs of scurvy because they do not eat their fruits and vegetables. Now, if we look at collagen, we see an interesting thing in that the third residue always passes through the center of this helix. So that's why you need glycine there. Glycine is small enough that you won't have steric hindrance to go through this helix. And also, if you take this helix and look downwards, that is, position the helix in front of your eyes and look straight down, what you'll see is something like this, where you have intrastrand hydrogen bonds. So the carboxylic group of a backbone interacting with the amine to form this nice network of hydrogen bonds. And this hydrogen bond network is one thing that makes collagen so strong. Now, if you talk about most proteins would be globular. So most native folded proteins are globular. And these proteins contain a lot of different types of secondary structure, both alpha helixes and beta sheets, but they can also have irregular or unique secondary structure. And if we don't have a nice name for that, we call it coil. Now, you can have different types of coil. If you have what's called a random coil, that means you actually don't have structure. It is adopting different shapes all the time, and you can't get an actual structure. A coil does have actual structure. It's just not classified as an alpha helix or beta sheet. Now, when we look at secondary structure and we compare, okay, which protein or which amino acids are in secondary structure, we see some patterns. So what here we're showing in this table is the propensity of amino acid residues to be in alpha helix or beta sheets. Basically, it's if you randomly look at an amino acid, what propensity do you see? Numbers greater than 1 more often, numbers less than 1 less often. What you see is that proline and glycine don't really show up in your secondary structure. And the reason for that is proline is what we call a secondary structure breaker. As we saw in the alpha helixes and beta sheets, you have this hydrogen bonding network. Now, proline, since it actually bonds to its own backbone, doesn't have the ability to form hydrogen bonds that well, so it's not going to be in secondary structure. Glycine, if you remember back on the Ramachandran plot, it adopts a wide number of different phi-psi combinations. If you're in secondary structure, your phi-psi is rigid, so it is entropically unfavorable for glycine to be in a secondary structure, generally speaking. While something like alanine is very common in your alpha helixes. Phenylalanine is common, so is isoleucine in your beta sheets, but tyrosine as well. And that's it for this video. I will see you in the next video.